Thanks for having me. It's let's see if I can get this going here. My name is Mary Foss, and I'm from Weber State University. And this is a paper that was written by my advisor, Yucheng from South Dakota State University, and also a mentor, Shantia Yarahmadian, in the Department of Applied Mathematics at Mississippi State University. And this really was a fun project. What we did is we looked at creating a mathematical model of learning based on reaction kinetics. So we wanted to understand the learning process. This is a lofty goal, and we wanted to use the tools of applied mathematics to do so. So in general, learning is a process that's very important, but it's really not well understood. We can establish that it requires concentration, time, focus work, as well as mental well-being. And there have been models that have been created that attempt to capture the learning process and the simultaneous process of forgetting. And it was our goal to not necessarily create a learning model, but at least to imagine that such a model could be created. So a little bit of background, the Atkinson and Shriffrin theory was developed in 1968. And this is a lot of what the learning models are based upon, and it's related to the storage of knowledge in the form of memory. There have been, like I said, a number of mathematical models that have been created from this and developed by researchers in psychology, science teaching, mathematics, and others, and they're looking to represent that learning process. Most of these models are empirical models that were developed by fitting input variables to numerical results. So they really don't explain the physiological process that occurs when an individual learns. However, the idea that there could be an advanced numerical model that could represent the biochemical processes that explains how an individual understands is obviously pretty interesting. A number of people have attempted to do this. There's a lot of theories that have come out of this. And all of these models have motivated a response and criticism also to the logic in their development. So really, I'm just trying to highlight that there is nothing out there right now, and this isn't it either. So researchers are motivated still to develop a model and build upon the process of learning as a probability and relating it to other biological processes and plateau phenomena. So there's a few researchers here, Frederick and Wahlberg, Aldridge, empirical studies, and all of these models, they really do contain some elements of learning, but none of them can completely capture the multi-dimensional process of learning due to that lack of understanding of that biochemical and neurological response of learning. Most of them rely upon empirical data for calibration rather than constants that are inherently deterministic. So let's look at reaction kinetics. So taking this cliche that life is chemistry, taking that to heart, the idea with this is we're going to examine if learning happened similar to a process of molecular biology and biochemical kinetics, which are similar to our enzyme kinetics, nerve signal propagation, that there might be an analogous model to learning. And that we could look at these models with our mathematical application tools and come up with the differential equations and evaluate them. So in a nutshell, this was our methodology to develop and explore the learning process based upon reaction kinetics, develop rate equations and conservation laws based upon those models, and then solve the related first or second order differential equations to develop rate equations for the model variables, and then evaluate those derived equations using analysis tools of applied mathematics. Now, these are time series plots, phase plane plots, and evaluate for stability. Now, I don't have a ton of time, and these topics we could really spend probably a couple of semesters on, which is what I did. So we'll just barely touch base on these models and see what conclusions can be made. So our very first model is very simple and easy to understand. So this is learning as a unitary reaction. It's our simplest model, and this is where you have some information, X, and then after a certain amount of time, the learning has occurred within the individual. So now that information exists within the individual. So we come up with the, let's see, right, I can't get it on that screen. We come up with this equation and the related time series plot. But you can see that there's several significant features in the learning process that this model overlooks. This model assumes that all information presented is consumed at the same rate and translated directly into knowledge, and the reaction happens until all information is consumed. So this is clearly not how it works. A student may learn one topic at a different rate than another, and then this model also doesn't account for any type of memory loss. And so we will kind of look at that, build upon this to create other models. So here's a building upon that, learning as a binary reaction. So in a binary chemical reaction, you have two different molecules combining to form a new product, X plus Y equals Z. In this model, we're assuming that X is information that you are exposed to in sensory information, so maybe listening, and Y is information that the individual interacts with in a dynamic way. So maybe you're practicing or you're actually doing something, maybe you're doing homework. So this model, again, has a lot of flaws in it. It presumes that no knowledge can be gained from sensing alone, and the application of that information is necessary to be converted into knowledge. This is clearly not the case for a lot of learning, but it probably does apply to certain fields. So for example, in the practice of medicine, you might be able to read volumes of books on surgery and maybe even observe others performing surgeries. But if you go to apply this learning by performing a surgery, you might fall short with the learning that was necessary. So practice does have a role. One thing that is interesting in this is it resembles a logistic model, which is consistent with many of the other prior mathematical models of learning that have been presented. So in this model, the equation you can see here, C is, you can think of it as the learning capacity of an individual. And the term KC is now going to be representing the intrinsic learning rate. So what's interesting here is, and this is kind of the goal, is to look at the stability of the model. And so these are the conditions that you can see on this graph. If I can get can't get my cursor to go over there. But we have two conditions here. The one where the curve intersects 0, and this is considered unstable. And the curve, in this case, where our information X is equal to 1. In this case, C was set at 1. So this is where the information is equal to the learning capacity of the individual. So just a really quick background on this. In applied mathematics, stability is a condition in which a slight disturbance in a system does not produce too disrupting an effect on that system. So this is a potential solution to a dynamic differential equation. However, this model, of course, is not perfect. It doesn't include a way to capture the memory loss. It also assumes perfect translation of information into knowledge without any errors in conceptual understanding. And this is counter to what we understand about the learning process. So moving on to the next one, we have this learning as a reversible binary reaction. So the goal of this was to capture that memory loss with learning and using an analogous chemical reaction, which is this reversible process. So we have here X plus Y gives us Z, and then also Z goes back into X plus Y. And the terms K1 and K negative 1, these are the rate constants that would be associated with that process. Okay, so looking here, this is our phase line diagram. This is assuming positive C constants. We see that there are two equilibrium conditions. So this is where our graph crosses that 0 axis. The one where it's -1 is unstable, but we do have a condition that is stable. And also it's important to note that there's conditions where the change in knowledge, so this is our dx dt, is positive or negative, implying that there's a theoretical ability to optimize the rate of change of knowledge. However, just like our other models, we don't have a way to identify short-term versus long-term knowledge. This is one of the elements of the Atkinson-Shriffrin model. And then we don't have a way to distinguish different methods of presenting the information. So the model doesn't differentiate effectiveness of differing methods of teaching. So we have to improve upon this one also. Which brings us to learning as a reversible binary mass action reaction. So you can see some changes with this. We have some coefficients in front of each term, x and y. So x, again, this is our sensory information. Y is our interaction with the information. And we have W and Z. Now, W will represent our short-term knowledge, and Z is going to be our long-term knowledge. And we have, this is reversible still, so K and K1, these are our reaction constants. So we have one equilibrium condition here that is stable, but we have a very narrow range with where the change of knowledge, and this is dz dt, is positive, and the total knowledge is positive. Like the others, there still exist several flaws in the philosophy of this model. So this presumes that short-term and long-term knowledge are gained concurrently, which is counter to the Atkinson-Shriffrin theory. And then there's a lot of constants. So each of those coefficients would be very difficult to be calibrated from empirical data. And it makes the equations quite complicated in a hurry. So this graph, I assume all of those coefficients were 1, just so we could come up with a graph. Okay, so moving on to that, we have learning as an enzyme kinetic reaction model. So this is, with an enzyme kinetic model, you have an intermediate complex created before the final product is formed. So this is a useful analogous model to capture the change from information from short-term memory. And this is our variable W that's transferred into long-term memory, which is our variable Z. So in this case, X is still going to represent the information consumed, and Y is the information that you're interacting with. And with this, we have a new way. So this is, we're examining these graphs with phase plane plots. And this is how you examine parametric equations. It's on the phase plane. So the equilibrium or steady state conditions are represented by critical points. Without going into a ton of detail here, you can see this one on the far left. There is a critical point. All of the solutions converge. And that shows you where there is some stability. So we have a stable node between the sensory information X and the short-term memory W. However, there are no stability points between any of the functions of Z, which is our long-term memory. So this could be supported by a hypothesis that forgetting is a constant process and that no knowledge can be retained indefinitely. However, there is some research related to trauma that shows that it can be passed down through generations, so that might be counter to this model. The other weakness of this model is that there's no process that describes the decay of long-term memory, and there isn't a process in which the short-term memory is bypassed and the long-term memory is formed initially. So both of those we would want to represent in a really accurate learning model. So the last one we examined was the learning as an enzyme kinetic reaction with decay. So this is building upon the last. So you can see here, we have our X and our Y. This is our information converted in, which is a reversible reaction to short term, another reaction to long term, and then a decay reaction here where that Z, that long-term knowledge, is breaking down. So this is capturing the long-term memory loss and is really a critical part in the accurate learning model. So in this case, all of our variables are the same here, but you can see that there's some interesting graphs that we get. So the very far left and the far right graphs show a stable node between the sensory information, which is our X, and the short-term memory W or Z respectively. And this one in the middle, it shows the presence of a stable spiral. And this is what this shows you is an imaginary component of the solution. So what that really means is that the solution to this differential equation would be in the phase plane. So it would be in like a frequency rather than a numerical value. And this could be one possible explanation why we haven't come up with a learning model, and because we're researching in the Cartesian plane of analysis, and maybe the imaginary plane or the phase plane needs to be examined more carefully. So in conclusion, human cognition and consciousness learning. These are very considered and studied and yet really mysterious topics. The goal of our paper was to use the tools in the field of applied mathematics to gain an understanding of the behavior of 6 different theoretical learning models that are deterministic instead of stochastic in nature, and all based upon chemical or enzyme reaction kinetics. So all the presented models here have weaknesses, but they do capture elements of what we understand about learning. And I think, I can conclude personally that we are either not equipped with the suitable cognitive capacity to fully understand the mystery of life, or we don't have a thorough enough understanding on biological processes yet to really create a complete mathematical model. So are there any questions?